So here we have a differential equation problem. We're asked to find the particular solution, so we need to go through the full process. Separate the variables, general solution, which has a constant, boundary condition, y is 6, x is a half, gives us a particular solution. And as we found yesterday, we've got to be prepared for a little bit of log-based gymnastics. So, you know, it's fiddly. It's fiddly. The first thing I would recommend you do is factorise the right-hand side, and then do the thing where we get all the y's on the left-hand side and anything with an x on the right-hand side. You're going to be immediately faced with a bit of a puzzler on the right-hand side. In fact, you might find yourself asking, how on earth do I integrate that? Which I'm hoping will give you a bit of a clue as to how you do it. I'll give you a minute to get somewhere with this. Now, the other day, I was a bit of a doofus by trying partial fractions, when I didn't need to. And when I worked through this example beforehand, I did exactly the same thing again. So don't be a doofus. Hopefully, you're getting used to recognising a difference of two squares. And hopefully, unlike me, rather than trying to write that in partial fractions, you realise that actually this and this are the same thing. So you end up with two things that become logs, ln's. Just be careful on the right hand side, because that gives you the ln of 1 minus x divided by minus 1. And then remember what we did yesterday with the constants to make it a little bit easier. So I've integrated that to give me ln of y. Y is the variable. I integrated that, still a log, 1 over a linear expression will always be a log, but this time I've got to divide by what you get when you differentiate the bracket, so I divide by -1, which makes it minus. I then rewrote c as ln of something else. It's still a constant, and it just makes this next step easier. Now, I don't know how you approach this next step, but here's what I did. I imagined those two things written the other way around, so it's ln of a minus ln of 1 minus x, which meant I could use the second log rule and write it like this. Now you could have done ln of, you could have brought the minus sign up here and changed that into the -1, but it's much easier, I think, to do that. And we did that the other day with partial fractions as well. So I'm flipping those two around. So I've got the log of one thing, take away the log of another thing, which means I can write it like that. And then I e both sides. This is a particular solution. And in this case, I could substitute the values in because it doesn't give me any negatives in the modulus signs. However, I hope you agree, this is a whole lot nicer. So I'm waiting until this point. Now I'm going to substitute in my values and work out the value of A and then rewrite my answer. So by doing the log gymnastics, we just end up with something that's a little bit nicer to deal with.
So,
Yes?
how does it go from plus C to plus LA?
Right. This is a constant. The log of another constant is still a constant. So I've just renamed my constant as the log of something.
Right. Okay.
And I'm allowed to do that. C is not the same as A, but it doesn't really matter. All I'm doing is saying, right, I know I could potentially have a constant here. I can call it what I want. If I call it the log of something, I can use the log rules.
Okay.
So it's just a little trick that we use. So I separated the variables, got a general solution, did some log gymnastics, which are complicated. I'm not saying, oh, come on, really should be able to do this. This is blooming complicated, getting from here to here. The only good news is that it happens a lot. So hopefully, if you've done, by the time you've done a few practice ones, you sort of see it happening. Okay. I'm going to get out some formula books here. Again, we want to separate the variables, so we've got everything with a y on the right-hand side, the left-hand side, sorry, with a dy, everything with an x on the right-hand side with a dx, and then we integrate both sides. And I guess the question is, why have I just given out formula? page 7, what you're looking for. So this time when we separate the variables, all I had to do was divide both sides by y. So we get this. And left-hand side, nice and easy. Right-hand side is a product. So we use integration by parts. So remember, integration by parts is a you know, it comes from the product rule, but when we load up our windows, we don't put things here and here like we do with the product rule. We put things here and here. This thing we differentiate, so it makes sense to put the x there, because that becomes a whole lot simpler when you differentiate it. This thing we integrate, and when the sine becomes cos, becomes minus sine, becomes minus cos, when you differentiate, so integrating. So see if you can find the rule on page 7 and see if you can do the right hand side using integration by parts. And you've got a boundary condition, so hopefully you can get a particular solution. Interestingly, it doesn't say how it wants the answer this time. It doesn't say it wants it at y equals. But I'll leave that with you. Integration by parts, it's on page 7 in the formula book, so you don't need to remember it, you just need to remember where in the windows you put things. So I put x here, sine x here, fill in the windows. Integration by parts is x times minus cos of x, which I've chosen to write as minus x cos x. Take away the integral of those two things multiplied together, so that's minus cos x. And because minus out front of the cos x is effectively minus 1, I can pull that out and turn that into a plus. Don't need to do that, we'll get the same answer in the end. So I'm only having to integrate to cos, which gives me sine. So I end up with now there's a really good reason why I don't need to do the log gymnastics when I now substitute in my values. It's not just that I don't get any minuses in my modulus signs, but it's just that the ln of 1 is 0. So it makes sense in this case just, plus c. It makes sense just to leave it in ln form rather than eing it. If we did e it, we'd still get the same answer. So I'm going to make x equal to pi over 2 in that and work out the value of c, and then I'm going to leave it in ln y equals form for my final answer. Always going to do this by doing pi over 2 arrow x firstly to save me having to type pi over 2 lots of times. That gives me my general solution. Why have I left it in ln y rather than going through all the log gymnastics? 2 reasons. They didn't ask for it in y equals form, and substituting values in at this stage didn't create any problems with minuses inside the modulus signs. So it was perfectly okay to leave it like that, and I'm fairly sure they did the same. 10. However, if you chose to write it as y equals e to the all of this, perfectly okay. Perfectly okay. It would always be an or equivalent type question. Now we could spend all day looking at different examples of this. We don't have the time, so I'm going to recommend very strongly that independently you have a go at question 12. Question 12 is probably a bit more like an exam question would be, because if we jumped straight in at part B, when we separate the variables, we'd have a 1 over y dy on the left-hand side, and we'd have 8x minus 18 over this on the right-hand side. And integrating that would require partial fractions. So they always, in part A, they get you to do the partial fraction bit first. So it's almost like them giving you a bit of a hint that this question is going to need partial fractions. So that's quite a good question, and we'll perhaps have a review of that tomorrow. So I strongly recommend page 325, question 12. You have a little go at that one before next lesson. And I'd be very happy to spend some time going through some more of these after school on Thursday. So remember, tonight is the sort of more directed stuff. We're doing some straight lines and some circle stuff. But Thursday I'm going to stay around and happy to go through any exam questions or anything that you're stuck on. Let us. No, I didn't mean to do that. Let's move on. We're sticking with differential equations though, so you might think that's too quick. It's okay, we're still with differential equations. We're just moving on. Now this looks a little bit like the second example I started with in yesterday's lesson. We started with a dy by dx expression where we had x on the right hand side, so we could just integrate without having to do any separating the variables. And then we did one that looked a bit like this, In this case, it's dp by dt, but the variable is p. So the approach we used yesterday was to flip it on both sides. And if I did that, that would give me the ln of 3p divided by 3. I don't really like though having too many different techniques up my sleeve. So instead, when faced with a problem like this in future, I'm still going to use my separating the variables approach. I'm not going to use the flipping approach. The flipping approach will work. But instead, here's what I'm going to do. Leave the dp there, bring the dt up here, leave the 3 where it is, and divide both sides by p. And obviously, you know, that dividing by p thing is problematic if p could be 0. So we're looking for some reassurance. Initially the population was 8. So you'll find in exam questions there'll always be some sort of reassurance in there. Now I could have taken the 3p across and had 1 over 3p. Generally though, it's easier to leave that coefficient there. We'll get the same answer, whatever. So I'm now ready to integrate both sides. I've still used separating variables, even though actually there are no t's to be seen. This is going to give me the ln of p, and this is going to give me 3t plus a constant. Now I've got a boundary condition. Initially, it's a magic word. But do I substitute it at this point, or am I better off eing both sides? Well, let's look for something in the question that gives us a bit of a hint. They don't want it in terms of LNP, they want it in terms of P. So at this point, I'm going to E both sides, and that just removes the need for the modulus sign. And then the trick that we talked about, here I've got e to the 3t plus c. Well, I know that, you know, when we were doing indices back in the day, I add indices when I'm multiplying powers of the same thing. So here, that must have come from that. So we've met constants that are just letters on their own. We've met constants that are ln of something, ln of A, ln of B. Now we've got a constant that's e to the c. And I don't really care what c is. I just want to know what e to the c is. Let's substitute in my values. P is 8. E to the power of 3 times 0. Well, anything to the power of 0 is 1. So that's 1 times e to the c. Ah. There we go. I don't care what c is, I just want to know what e to the c is. So I can rewrite this or now we've got that by going through our process here, but actually I should have known all along that A was going to be 8, because in any situation with exponential growth, this is the initial value, isn't it? So when we did exponential growth back in year 1, that coefficient out the front was the initial value, what you get when t is 0. So I should have known that already. It's reassuring that I got that correctly. Right, so now we need to work out at what what the population will be when time t is 2. So we've got a nice formula now, we're just going to substitute that in. And at what time will the population be 8,000? So we're going to use that formula for both B and C. And then you've got one of those annoying 1 mark questions, which we'll have a chat about. So we're going to use that formula. In part B, we're going to substitute in the value of little t. And in part C, we're going to substitute in the value of big P. Big P needs to be 1,000 times the initial value, which was 8. Slightly odd question, but oh, nearest 100. And the time is in hours, so happy with that? Anyone want to suggest what the limitation would be? Well, whatever it is, we'll run out of space or food or, you know, I mean, microorganisms. If it's in a petri dish, they'll get to the point where they've filled the dish, or if they're, you know, growing on a surface, then they'll fill the surface. So there's always sort of limitations at the top end with these sorts of models. Now, we'll give you a chance to try a couple of those for yourself, but I think, can I go through onto a second, slightly harder example? So here we've got a tank holding water. The diameter of the tank is 20, the height of the water in the tank is h, and water is flowing out of the tank. Water is flowing out of the tank. So can I get you to write down a formula for the volume of water in this tank? You're going to need to use the 20, you're going to have to use pi, and you're also going to have to use h. So the volume of the water in the tank. So they're expecting you in this question to remember how to work out the volume of a cylinder. Spoiler alert, you're not going to use, or they're going to use the 20, you're not going to use 20. Once you've got your expression, differentiate it. That's going to give you dv by dh. Remember, pi is a constant, so that's not a variable. So area of the end times the height, area of the end is pi times the radius squared, so you get 100 pi times h, and if h is the variable, when we differentiate that, we just get 100 pi. Why have I done that? Well, we've got to get an expression for dh by dt, and that seemed to be a sensible place to start. We're also told water is flowing out of the bottom of the tank. So that is the rate at which water is flowing out. The rate at which is flowing out is proportional to the cube root of the volume. That means it's equal to some constant times the cube root of the volume. And it's flowing out. So this is going to be a negative. I don't want k to be negative, I want k to be positive, so I make minus k. We did do that when we were talking about rates of change question before. So see if you can build dh by dt with the two expressions that we've got so far. Probably won't give you the thing that you've got to show it's equal to, because you'll have, well, see what you think. I'm regretting a decision I've made. I'm going to call my constant something else for now. Sorry. So I do this multiplied by 1 over that, which gives me this. Still not getting me there. V, I can replace that, can't I? I can replace with now. When we deal with surds, we know that the square root of two things multiplied together can be split up as two separate square roots. Does that apply to cube roots? It does apply to cube roots. So what I can say is that I get, sorry, so I've just split that cube. It's not c cubed, is it? It's minus c times the cube root of, I haven't written it very clearly. So I've split that cube root up into two cube roots multiplied together. And then all I've done, or all they've done, is they've said, well, although it looks horrible, this thing here is a constant. There aren't any variables in there. So let's just replace it. Let's call it k. So we get as required. Now that's a bit of a fiddly thing to do, and because of that, they give you that in the first part. So even if you can't get that, you've got that as your starting point for part B. So we're basically just saying that's a constant, so let's just call it something else. And that's why I was silly with my choice of k to start. And I think, did you say, how on earth would you remember to do that?
No, I just think I wouldn't realise I'm trying to do well.
Yeah, so the good news is that you wouldn't be locked out of the rest of the question. You've got the starting point for part B. So let's now, taking that as our starting point, let's now separate the variables. Now I'm going to leave the minus k where it is and bring the dt up. I'm going to move this down here. So it was h to the power of a third. It will become h to the power of minus a third, because it'll be 1 over h. And I can integrate that. Have a go. See if you can separate the variables. So we're now on to part B, trying to integrate this. I'm saying again, this is really hard, really hard. I'm not doing this because it's easy. Minus k is a constant, so when I integrate that with respect to t, I just get minus kt. This I'm hoping you can do by increasing the power and dividing by the new power, remembering that the denominator pops to the top. Cube root is the power of a third, but 1 over the cube root is the power of minus a third. When you integrate, you increase the power by 1. The process you now need to go through is to get the h on its own, because that's what they've got here. So I'm going to divide both sides by 3 and multiply both sides by 2. And I'm going to put that as a number outside. I'm not. I'm going to multiply it out actually. I'm then going to square root, because the power of 2/3 is the cube root squared, so I'm going to undo the square root by, undo the squaring by square rooting. Power of a third means the cube root. I'm going to undo that by cubing, which should give me something that looks a little bit like that, but of course we know that they are very happy to replace something which is a constant with just a single letter. So you won't have p's and q's, but you will have things which are constants. So I'm going to multiply by 2 and divide by 3. I'm going to multiply this by 2 and divide it by 3, multiply this by 2 and divide it by 3. I'm then going to square root, I'm then going to cube, and that should get me to where I need to be.
Do you need to worry about C?
Yes, that's still going to be there. So when I multiply by 2 and divide by 3, that's going to give me...
So it's not like the kind of thing like, C is a constant, so we might as well just leave it as
Well,
C.
yes, we can do that. We can do that as well, and we are going to do that right at the end. But I'm going to rewrite it as 2/3 times C. But yes, you're absolutely right. You could do that. So I am there. I'm going to rewrite it up here because I know this is what I've got. So to turn that into their form, I'm going to call minus 2/3 of k, I'm going to call that, well, sorry, 2/3 of k I'm going to call q. So that's going to give me minus qt. And 2/3 of c I'm going to call p. So I've sort of got what they got. just by saying, yeah, that's a constant, so we can rename it whatever we want. Two constants, so I'm hoping I've got two boundary conditions, because I'll need to solve simultaneous equations to work out the value of P and the value of Q. I'm hoping that you can see here that we do have that. We do have two pairs of T equals H equals, remembering that the word initially is like a magic word. So go on, see if you can substitute the two pairs of boundary conditions in and solve the simultaneous equations. Your calculator will solve simultaneous equations for you, of course, or you can do it manually. Remember, this is the square root cubed, so to undo it, you cube root and square. So because t is 0, it's relatively easy simultaneous equations. You just got the first equation gives you the value of, you've just got to remember that to undo to the power of 3 over 2, you do to the power of 2 over 3. You cube root and you square. And if you did the last bit, well done, you get 16 minutes. Now, you know, that is probably about the hardest problem we'll do as part of our work on integration. So, you know, it's always hard to know how to pitch it. You know, we can't avoid these questions, but you've got to set any work you do on tough exam questions in the context of grade boundaries, haven't you? And we know that, you know, the grade boundaries reflect the difficulty that the questions offer. But, you know, as I said, even if part A was something you couldn't do, can't be good. And even if you couldn't get anywhere towards here, the act of separating the variables would get you marks. And you've got this here, so even if you can't do part B, you can do part C and D, because you can start with that and substitute the values in. So, you know, they're walking you through this rather than it just being a 10-mark question where if you can't start, you get 0 marks, and that's hopefully what you'll be able to do in the real thing. So we are running short of time, so my recommendation is on page 328. Question 1 is a relatively straightforward question, a bit like the first of the 2 examples we did this lesson. And then question 4 is a bit more of a fiddly question. You might, don't get hung up on part A of part 4, you could have a go if you want. But I would like to, I'd like to look at question 4 next lesson. So if we could have a go at those 3 questions I've circled. One on page 325, which involves partial fractions, and then 2 of these are referred to as modelling type questions, so page 325 and 328.